All right, what's going on, everybody? Today we're going to be doing another LeetCode problem. This one is going to be called LRU cache. So they basically want us to design a data structure that follows the constraints of an LRU cache. LRU meaning least recently used. So basically, we're going to be storing a bunch of keys and values in a way such that there's a fixed capacity. um, Obviously we need to be able to get and put keys in O of one, big O of one, or constant time complexity, but we also need to be able to evict the least recently used key value in constant time. So obviously this is going to be a little more sophisticated than using a just a map, right? Because we need a way to keep track of the least recently used key in constant time. We need to be able to evict it. In constant time, and just basically maintain some relationship between all of our keys and our values, to know which ones were used more recently and which ones were used least recently, right? It's kind of like a spectrum. So so anyways, yeah, let's just whiteboard this a little bit to understand basically the data structures we're going to use for the implementation. So we there can be a max capacity here, right? So I'll say M for max capacity. Let's say that, for example, that is 2. So we're going to be using a hash map, right? Where the keys are integers because the keys are just integers for this problem. As you can see, we have a key. So like this is for this put operation, we have integer keys, right? And it also says that here, integer values also. But we're going to be doing something slightly different here. So grab first, these will just be, blank, empty. Nothing will be here, but the values in our hash map are actually going to be node pointers. So we're gonna use a we're gonna use basically a doubly linked list to keep track of the least recently used key value pair. So, and it'll be doubly linked, and basically the left side of the list will be marked by this left dummy node. And then the right side of the list will be marked by this right dummy node. At first, those are just pointing to each other, right? Because there's nothing in the list, and doubly linked, so technically there would be a previous pointer here that points to null pointer, and a next pointer here that points to null pointer. So basically, the LRU values are going to be toward the least recently used value, like objectively the most recently used value, is going to be all the way adjacent to this left dummy node, and the most recently used value will be adjacent to the right dummy node. So, and then it's kind of like a spectrum, like I said. So second to least recently used will be after that, and then by same situation on this side. So I'll just mark this. So LRU is going to be this way, right? Least recently used, and then most recently used. Hopefully you can tell that that is an M. Most recently used is going to be this way. So let's go over, so if we were putting a value, we're going to need some helper functions, obviously, because if we're every time we're putting or getting a key value, it's going to need to get updated to most recently used. So we're going to have to basically remove it from wherever it is in the list. So we need to be able to remove any node from the list in constant time and then insert it in constant time. Obviously, it's pretty easy if you know which node you're working with, because you're just repointing pointers, right? So let's say we had to insert the key value pair, like key 2 value like 3. So we would allocate space for a new node. So let me erase this. The key for our hash map is just going to be 2. And then we're also going to we're going to allocate space for a new node here. So like so. And we'll create a struct for nodes, for our doubly linked list nodes. So let's say, we just allocated space for this node. We are pointing this key to this node. The value is going to be a pointer to a node, right? And now we need to insert this node into the list. So we're going to have an insert helper function. Basically, the way we're going to do this is for insertion. Let's just so I for insert, we're going to need a previous pointer, and we're going to need a next pointer. So when we're inserting something into this list, we're always going to be inserting on the right side of the list, right? Because we're going to be inserting more the most recently used node, right? So it needs to be over here. So previous, in this case, there's nothing in the list yet, so this will just point over here. Next, we'll always point to the very right side when we're inserting. So now at this point, we need to point this node, right? Because it's going to have some pointers, but they're both null pointer at first. This first, it's obviously going to point next to this right pointer, right? And then the previous pointer will go to whatever's previous of the right node. And in this case, again, it's this left node. So that'll go there. And then we just need to repoint these two pointers here, right? So this one. So basically, whatever's previous here of the right node, we can now point to that node. And then the right previous pointer can get pointed to that node. So that's in a nutshell, basically how we would insert that there. Now say if we were removing this node, right, it's a little bit simpler. So I'm going to do the same little drawing or similar drawing here we're going to have a remove. By the way, these are just helper functions, right, to help us deal with this list. So when we're removing a value, we need to be able to do that at any node in the list in constant time. So same concept with the previous and the next pointer, right? Except this time the previous will be just whatever this node is pointing to previously. So here it'll be the left pointer. Next will be whatever node is pointing to next. So the right pointer. Now, basically, we can just reroute this, whatever its previous pointer is pointing to next needs to be pointing to next. Whatever next is pointing to previous needs to be previous. So this and this will get erased. And basically, just skip over that node, right? And we'll handle deallocation not in this function because when we remove it, we might want to recycle that node, right? And just insert it at the most recently used position. So we're going to deallocate manually, basically, and it's not going to be attached to this remove function. But we are still going to deallocate all of the memory that we are no longer using, so we don't have any memory leaks. So yeah, let's just go ahead and get into the code here. So I think this is should be sufficient demonstration of the data structures we'll be using. So first thing we need here is just a struct for our doubly linked list nodes. So I'll just call that node, and each node is gonna have a key and a value. We should call that val for short. We're also going to need for our doubly linked list nodes, basically just node pointers. So to the next node and to the previous node. And we need a constructor for this, right? So this constructor, for simplicity, in practice, you'd want to have several different constructors to work with, but we'll just have a constructor for our key and our value. I'll call the value, the parameters. I'll just prep it. I'll put a underscore before the name of the variable that's getting assigned for code clarity. So key will get set to underscore key. That'll be the first param. val will get set to underscore val second param, and then our node pointers will both just be null pointer at first. So that should be good for our node structure. So these will be in our doubly linked list. So first, we're gonna need some private data members, right, for our LRU cache. So we're gonna be implementing that linked list from scratch, right? So the left dummy node that marks the least recently used key value needs to be kept track of, right? So we'll just do that for the left node. We need to do the same thing for the right node, for the on the side of the list that has the most recently used key values, right? And then we also need an integer value, right? Because this can have a max capacity. So we'll just call that max. And then finally, we need our hash map, and we'll use an unordered map for that. So with key values and then node pointers, or key integer keys, and then node pointers for the value, right? And I'll just call that map. So that should be it for the private data members. Let's go ahead and take care of this constructor. So our constructor is just going to take the capacity. So we can set max to whatever that capacity is. Our left, let's see. Yeah, we need to initialize these dummy nodes, right? So we're going to create space, allocate space for a new node here. The values for these nodes obviously don't matter, but we're going to pass in zeros just because that's our only constructor. It takes 2 parameters. So we'll obey those rules and pass in parameters, even though we're not technically using them. So that'll be our left dummy node and our right dummy node. And then we need to point left next to the right pointer at first, and then right previous will be pointed to the left node at first, basically just to connect those. There's nothing in between them at the beginning, and we don't have to do anything for unordered map. That space takes care of itself because it's a built-in, it's an STL data structure. So let's go ahead and implement this put method first. So the first thing we need to do when we're putting a key value is basically we just need to check if we'll disregard the max capacity at first, and I'll do that once I've implemented the basic logic here. But so we need to check if our map contains that key, right? Because if it does, we can just recycle the node that we already allocated space for. So if the map does contain the key, let's go ahead and get that a pointer to that node. So we can find it by just taking the value, which is, I remember, that's a node, a pointer to a node. So that'll be that node, and we can set its the key will be the same, right? But the value is going to change. The value is going to change to value, and we need to basically update its position to most recently used, and that's the right side of the list, remember. So we're going to have some helper functions. So let's actually declare those real quick. So those will be void. We're going to have a remove node function that takes just the pointer to a node that we want to remove. And we also want a void insert node function, and that'll have the same sort of parameter. We'll take a node to insert, pointer to a node that we want to insert. And I'll go ahead and implement these at the end. But so we're going to want to update the position, right, of this key value to the most recently used now, because we just inserted it, right? So we need to, being that we're recycling a node, we need to remove it from wherever it was, right? So let's go ahead and just call that remove node function. And then we need to insert it, right, to the most recently used position. So that'll be our insert node function. So that takes care of that. Now, if the node doesn't already exist in the map, we need to allocate space for it. So let's say node, star node. So we're gonna have a pointer. We're gonna allocate space for a new list node that has the key, right? And then the value. So the next thing we need to do, we don't need to remove it, right? Because it doesn't exist. We just need to insert it. So we're just gonna call insert node on that node. And then we also want to assign our hash map to that node pointer, right? And to the key. So map at key that we're inserting, we're just going to point that to the node we just created, right? So that's the case where we're allocating space for a new node. And before we do all this, remember there's a capacity. So let's handle that. So when do we need to evict the least recently used node? Basically, it's only when we are the key. So when the key does not exist in the map. So when the map does not contain key, when a map does not contain key, and right, and the size of our map is +1 is greater than that max capacity, right? Because we call that max. If we're about to put a key in there and it's going to exceed the max capacity, we basically need to evict the LRU key val, right? So and how do we know which one is the least recently used? Well, it's going to be all the way on the left side of our doubly linked list, right? So it's going to be adjacent immediately to the right of this left node. So let me make a note of this. So this is going to be LRU side of list. This is going to be MRU side of list, and we want to remove the LRU. So we're just going to go ahead and call remove node on. We're going to go ahead and call remove node on. We need to get that node first, right? So let's say node's pointer called LRU is going to be it's going to be the whatever's immediately adjacent to the left dummy node, right? So left next. And we can just remove that node, and we're actually going to be done with it at this point, and we allocated space for that. So we need to basically deallocate that space. And before that, we also need to remove it from the hash map, right? So map.erase LRU. And actually, this takes a key, actually. So LRU key, right? So that'll basically handle the LRU eviction. So we also need to implement the get function. And again, let me just remind that this is going to be O of 1, right? This will always be a constant time operation. And then this is also going to be constant time. So let me write that there to remind of that also. So when we're getting a value, we just want to check, right, if our map contains that value. So if the map contains key, and we know that key value exists, we need to update it, right, to MRU, right, which is it's the right side of list, because we're accessing it, that counts as using it and for an LRU cache. So we basically let's get a pointer to it. So node map key, and so we're going to assign this node pointer to whatever that node is at map key, and then we're going to remove node, right, to take it away from where it was. And then we're going to basically insert it back into the most recently used position. So insert node, and then we can just return the value at that node. And if we didn't find it, we can just return -1. Um, so that's it for the get and put functions. We also need to implement these helper functions, right? So for both of these helper functions, we're going to have some pointers to the previous node to help us. So node prev, node next, and we're going to use this in both. So let me just copy this. But let's take care of our remove node function first. So for our remove node function, the previous pointer is going to point to whatever's before the node, right? So node prev, that'll be the previous, and then node next, that'll be the next value there. And basically what we want to do, if we look back to our whiteboarding, remember basically all we did was just move the pointers for the previous, whatever previous was, like if we were removing this node, whatever previous was pointing to next needs to just be set to that next node, right? So previous next is going to become next, and then it's the same thing, right? For the next node. So whatever next is pointing to previously just needs to be pointed to that previous node. So next previous is going to be previous. And that's it for remove node. Remember, we don't have to allocate space because we handle that manually whenever we're done with a key value. And we'll implement the destructor at the end. So don't worry about memory leaks. We'll get to that. If there are any memory leaks in my implementation, please let me know in the comments. I don't think there are. I mean, I'm not finished yet, but but let me know if there are, right? Because everybody makes mistakes, but I don't think there are any. So anyways, yeah, let's write the code for insert node. So when we're inserting a node, the previous value is going to be whatever the rightmost pointer, right? Because whenever we're inserting a node, we want it to be updated to most recently used, i.e. rightmost side of list. So previous will be whatever right is pointing to previously. And then the next node will be the rightmost, the right dummy node, right? So so the first thing we can do here, or next thing, right? Because we already did something technically. So the next thing we're going to do is, we're going to handle what the node is pointing to next and what the node is pointing to previously, right? So we're trying to basically insert it like between these two nodes, right? So node next is basically just going to become right or next, interchangeably, but node next is going to be right, and then whatever node previous is going to point previously to whatever was ever before the right dummy node, right? So that's going to be prev. And then we need to basically point these nodes to the proper nodes, right? So previous, that's going to be what was ever before the right node. Whatever comes next of that is going to be, or what comes next is going to be the node, right? Because we're inserting it after that. And then the next node, right? Whatever's before that is going to be node, right? Because we're inserting that node between. So this I will admit, this is a little confusing here, but if you think about it enough and you do the whiteboarding on these examples, you should understand. That helped me. So these are constant time helper functions. Obviously, we're just repointing things around. So this is basically it. The last thing we need to do, and this is really important, so we don't have like a massive data leak here in this data structure implementation, we need to implement the destructor, right? So in C++, it's going to look almost like the constructor, but you just put a tilde right before the name of the constructor. And then that basically gets called whenever it falls out of scope in a program, right? So for destructor, we need to make sure we're deallocating space for any time we use the new keyword, right? So the first thing we can do is just delete those left and right dummy nodes. And then the last thing we need to do is delete all of the nodes in the list, right? So there's two ways you could do that. You could either iterate through the list before doing this, but what I prefer, I think the code for this is just cleaner. Just iterate through all the key values in the hash map. So for auto x, right, auto basically, um, instead of putting a type here, we can just use the word auto because we don't really know what type X is. I mean, I guess technically it's in some kind of iterator that has a key and a value, but let's not worry about that. We'll just use auto. And we're going to take that by reference so we don't have to like duplicate it at all. And then, so for auto X in our map, we're just going to delete all of those nodes. So we're going to delete X dot second. So second's going to be the value. So that'll basically clean up all that space and prevent memory leaks. So that's basically it for the code. Let me zoom out a little bit so we can see all of this. It's quite a bit here. I don't know if I can actually zoom out all the way without this looking really silly, but yeah, this is the complete code, right? So we have, let's just go over this again quickly. So, and let me run it too before that, just to make sure this is all valid. So yeah, and let me submit it also just to make sure it passes all of those test cases. So right, so yeah, beats 92% with runtime, 77% with memory. So it's a pretty efficient solution. Granted, I didn't write any memory leaks. Again, please let me know if I did. I don't think there are, but I'll leave the code in the comments too because it's long. But we have this node structure. We have these private data members. Again, we're using a doubly linked list and a map to keep track of the LRU key value. We have our destructor to make sure we free all the memory we're allocating. Two helper functions, right, for removing a node from the list and inserting a node into the list on the very right side. And then we have our get function, which basically returns a value based on the key, and then a put function that puts a key value into the LRU cache and also evicts the LRU key value if necessary, if we exceed that size. So hopefully this video helped you understand this problem better. If it did, please leave a like and subscribe, helps out the channel. So yeah, I'll see you guys in the next piece.